Spiking neural networks provide the opportunity for extremely low power operation while providing functionality that has been usually pushed into the cloud these days. So, Sumeet, could you tell us a little bit about the new Pulsar that you have?
Innatera has just launched Pulsar, which is the world's first neuromorphic microcontroller, which brings truly brain-like intelligence directly to sensors. Pulsar is designed to run spiking neural networks. It's the same neural networks that your brain uses to find patterns in sensory data. And what really stands out about these spiking neural networks is they're super efficient, they're small, and they're really powerful in the kind of things that they can do. And they've been very hard to reach for the last few decades, simply because they've been harder to train. The tooling has been missing. And this is something that we've been able to bridge at Innatera with the recent Pulsar launch. We're putting on the table fantastic new hardware, which is really specialized at running these spiking neural networks efficiently. And to add to that, we make these spiking neural networks accessible to traditional embedded developers by building Pulsar into a microcontroller format, which allows you to do a lot more than spiking neural networks alone.
So, one of the interesting points in this architecture is that you have both an analog and a digital version of the spiking neural networks. Why and how is that done?
All right, that's really great question. Now, our brains are inherently analog, and the entire point there is that the continuous time dynamics, which you typically see in biological neurons, allow spiking neural networks to have really the fine-grained temporal accuracy that they're famous for. But when you translate that over into the electronic design process, how you build circuits, it requires you to have a really wide design space. So the way we sidestep that problem is by creating these two different arrays. We've got the analog part, which is really low energy, which does well for signals at specific frequencies, signals at specific time scales. And then we've got the digital part, which has a much wider flexibility. It's more widely applicable, and applications can use that accelerator without really thinking too much about time constants and frequencies and so on. Fundamentally, the answer to that question is that the combination of the two provides developers with the flexibility that they need in order to pick the right tool for the job.
Now, those aren't the only accelerators that you have on this chip. There's also a convolutional neural network accelerator and a fast Fourier transform. Could you talk about why you have those on there and how they complement the spiking neural network?
Sure. Now, spiking neural networks themselves are computationally very powerful, and you can do a lot of operations, including the FFT, within an SNN itself. However, typically within a general application pipeline, it's very likely that you've got multiple different processing stages, and very often the kind of tool you'd want to use for each of these stages is very specific, and certain developers may want to use a CNN at one point in their pipeline, or may want to have a dedicated FFT block for a specific reason. By integrating these accelerators into Pulsar, we basically provide developers with a wide range of tools that they can pick and choose from when they're building up application solutions. It's not for us to dictate what you should be using for your applications. It's for us to really provide you a broad range of effective tools and leave it up to you to decide which ones you actually want to use.
Now, this is a full solution. Part of it is a RISC CPU. Could you tell us a little bit about its characteristics and about some of the peripherals you have on there and why this is something that can work in an embedded system by itself?
Sure. We use a very lightweight RISC-V CPU core whose primary function is to do all of the system management for Pulsar as well as to run the logic that typically exists outside AI models. And this really makes Pulsar an all-in-one package because very often when you've got to run an AI model, you've also got to do things around it. So for instance, a voice recognition system once it detects a word that's been spoken, it's got to do something, and that's typically done by the RISC-V CPU. And really, by putting it into the same chip, we allow the bill of materials for the sensor system to be shrunk into a smaller number of components. Outside of that, the CPU subsystem has a set of accelerators like the FFT accelerators that you called out, as well as a bunch of standard interfaces like SPI, I squared C, I squared S, that allow you to connect a very broad range of sensors to the chip. And today we already support things like radars, microphones, inertial measurement units, far infrared, you name it. I think at the moment, the only thing that we don't support are probably very high resolution cameras, but we've even got an interface through which you can connect an imager. So very broad application capabilities that come in through this heterogeneous combination of compute fabrics in the chip.
Now, if I'm a developer that want to take advantage of this new piece of hardware, what do you have in terms of tools that are going to make that possible?
We've got a really sophisticated software development environment that we call Telamo. And the design philosophy behind Telamo was really to make it simple for application developers to build and deploy solutions onto Pulsar. Telamo is predominantly interfaced with a PyTorch-based front end. So what that means is you build your spiking neural network models within a familiar PyTorch environment. The way we did that is by building in an extension to PyTorch that gives it all of the spiking capabilities that you would want to use in our chips. And therefore, you build, you train, you optimize your spiking neural network models using the familiar workflow completely in PyTorch. And once you've got a design point that you're ready to implement on the chip, you exercise the Telamo compiler, which really maps the network onto our chip without you having to understand any of what's going on in the hardware. Alongside that, you've also got a simulator, which basically serves as a stand-in for the chip, and you use that for all the design iterations and performance modeling that you want to do before you go into hardware. So essentially what you've got is a very complete set of tools that really makes it a seamless experience to go from an initial spec into something which runs on all of these different heterogeneous computing elements inside of the chip.
So if I want to get started with this, is there some development platform that I can take advantage of?
Absolutely. We've just announced a new developer program at Innatera. We're launching our Pulsar chips into the market, and through the program, we aim to make both the software as well as the hardware available to researchers, developers, hobbyists, industry partners the world over to build the next generation of neuromorphic applications that go onto these chips and out into the world.
Well, normally when people talk about these kinds of platforms, they talk about the applications at the beginning, but we're going to keep it here at the end. What type of applications is this going to be targeting? What capabilities can it take advantage of that we will find in these various embedded systems?
We predominantly think the main set of applications that Pulsar is great at are those in which power and latency tend to be a problem. And today, much of those you find in the smart home IoT space, in the wearables market, as well as in building automation use cases. So some of our star applications have been things like robust human presence detection using radar sensors, people counting using far infrared sensors. Both of these applications, one would typically find in something like a video doorbell, an automatic lighting controller inside of an office building, a door opener, all devices sometimes which are not really wired up, but actually battery powered, things like smoke detectors. And on the hearable side, we've got applications that improve sound quality by classifying the environment that you're listening to music in. And that's something which you would find inside a pair of headphones, for example. And some of our most recent applications have been activity trackers for something like your smartwatch or your smart ring, which is really looking at how you're moving throughout the day and really cataloging each one of your activities without needing your smartphone to be paired to the device. And something which is the closest to my heart is the ability to do cardiac diagnosis inside of a consumer device, something watching your ECG throughout the day and picking up that one odd heartbeat that occurred, probably once in a year, but that was the first warning sign that you were going to develop something dangerous. These are the kind of applications that we're unlocking today, and there are so many more which are coming up. As we're working with more customers, there are more exciting things which are really coming up. But generally, what's common to all of them is that there is a sensor producing data continuously. There's some kind of limitation of power or energy because the device is on a battery or in a very small housing. And generally, you need very high accuracy or very short latencies. These are the common, characteristics in all the applications that we work with today.
Well, very good. Well, thank you for filling us in on Pulsar, spiking neural networks, and applications on the edge.